All right. Here we go into the second video on shell method where we're going to see why shell method is so necessary sometimes for finding volumes of solids of revolution. So in this problem, it says find the volume of the solid made by revolving the following bounded region about the y-axis using the shell method. So I've given you the graph of it. We've got 4x minus x cubed. The x-axis, that's here, x equals 0 right here, and x equals 2. So it's this region in here. When we revolve this about the y-axis, an interesting thing would happen. If we were to solve this using it'd be washer method, we'd have a problem, right? And the reason being is our radius, if you look at it, that would be our inner radius, this would be our outer radius. You'd have to solve this in terms of y. Solving that function in terms of y is darn near impossible. So the shell method was invented for such problems as these. So what we do is instead of writing something perpendicular to the axis of rotation, we're going to drop a rectangle that is parallel to the axis of rotation, like so. And again, start out with your template. If you haven't watched the first video on this, you must. It's a must-see. So we know that the volume is equal to 2 pi times the integral from a to b of, and then we get the radius times the height, and in this case it's going to be dx. How do I know? Because that width is dx right there of that rectangle. You're going to be rotating this around, so you're going to end up with something like some kind of shell like so. Ooh, my goodness, that is a bad shell right there. Something like that, where you're going to have a rectangle that kind of comes out like that, and there's your shell, right? So now looking at that, your radius is going to be the distance from here to the axis of rotation. That is whatever x value you are currently at. So that's the radius, r. So r is x, right? If you're at x equals 1, that's your new radius. X equals 1.2, that's your new radius. So the x value is constantly changing. It's the radius that we're actually going to use as our boundaries. Our radius will change from it being darn near close to 0 to being all the way out here at 2, and we have a rectangle and a shell there. So that'll be from 0 to 2. Don't forget 2 pi. And then that'll be multiplied by what's the height. And this is the brilliant part. The height is very simply just the height of a rectangle, just like you would take when you're finding area of a region. That would be this top minus that bottom, and the entire time your rectangle is determined by 4x minus x cubed. So it'd be 4x minus x cubed minus 0 is just itself times dx. So that gives you the volume of all these shells that are just going to be slid inside of each other again and again and again. So that's it. That's your integral. Now it's just about integrating. So we have 2 pi times the integral from 0 to 2, I'm going to distribute the x, very simple integral, 4x squared minus x to the 4th, and that's going to be all times dx. All right, nice. We like this. The integral's not so bad. That's going to be equivalent to 2 pi times, this will be just 4/3 x cubed minus x to the 5th all over 5. Just a little bit of simple power rule action there. That's going to be evaluated from 0 to 2. I'm going to keep the 2 pi on the outside as a coefficient. So I have 2 pi times, when I plug in 2, I'll get 2 to the 3rd is 8, times 4 is 32 thirds, minus 2 to the 5th is 32, all over 5. And then I'll take that 0, and when I plug it into each of those values, you get 0. And when we simplify all this down, I get 2 pi times, this will be a common denominator of 15ths, so I'll have to multiply that by 5, so it's 160 15ths. I'd have to multiply top and bottom by 3 here, so it's going to be 96 15ths. And 160 minus 96 is 64. So that's 2 pi times 64, or 128 pi. That's quite a large volume. There we have it. That's it. Now, the integration actually ends up being pretty nice, but it's the setup that I want you to get down. All right, let's do one more. That's it. That's the shell method. I'm just going over a couple of quick examples for you so that you're in good shape on this. And then we'll do some lesson exercises. Set up but do not evaluate the integral that will find the volume of the solid made by revolving the following bounded region, the same one, about x equals 3. So this problem is a little bit different in that we're rotating it about a line, not the x or y axis. All right, so how do we deal with that? Well, when we rotate about that, again, you're going to draw on your rectangle. We're revolving it about the line x equals 3, and our rectangles need to be parallel to the axis of rotation to make a shell. So I draw that in, and I notice that then my radius is going to be the distance from any rectangle, right, to that axis of rotation. That's r. So in terms of my radius, That's this distance, but we got to keep distances positive. Always think geometrically. To be positive, we'll do right minus left. So that's 3 minus the current x value that we're at. 3 minus x. My overall template, if you remember, is 2 pi times r times the height of the shell, the height of the rectangle. And then that's going to be from a to b. All right, so here we go. So that's 2 pi times the integral from 0 to 2. Those are going to be the changes in our radii, as well as the changes in the heights of our rectangles. So the radius we saw is 3 minus x times, what's the height? Well, it's going to be the height of every rectangle that goes in this curve, and that's going to be this minus that, which is 4x minus x cubed minus 0. So 4x minus x cubed, and then multiply by dx for the thickness of the shell. And that's it. That's all. So you're asked to set it up. We don't need to evaluate it. You got the integration part down now, and if you don't, come back to chapter 4, of course. All right, that's the shell method. I'll see you in the exercises. Stoked for when you're there. Peace.